Good morning. I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm here today with Joe Canary. I think I pronounced that right. He is the principal scientist at Galois. Helena Hanshu, who is a Rambus Fellow, and Richard Newell, who is Senior Principal Product Architect at Microsemi, which is now a microchip company. Okay. Now that we've gotten through that, let's get into some of the meat here. We've heard a lot about open source hardware. Things are supposed to be much better in the open source world. Is open source hardware really more secure, or does it simply expose vulnerabilities on a much wider scale to more people, and particularly with published interfaces? And any order here, guys?
Okay, I'll take that. And we deal a lot with government and defense customers. And I would say they have a tendency to believe that absolutely everything should be secret. So they're, kind of a leaning towards that direction. I take a little bit more of a middle ground view, which recognizes that complex systems are going to have bugs. And so in that case, secrecy can actually improve your security. But simpler systems can be perfected by being open source and being improved until they're protected. And any real security system has to have layers that include some of these simpler elements to protect the more complex ones, which are eventually going to fail.
Yeah, I think I would like to add on top of that when you open source things, when you publish open specifications, that gives everybody an opportunity to look at it, to review it, to come up with comments, feed it back to the community that put the specs together. As a group, you can, advance, maybe not faster, but better. You have more eyes, more hands. Everybody is able to give you constructive feedback, and then you can work together to make it better. So that means you start from something that's open and published, and then you evolve it together by adding things into the specs or by writing guidelines or white papers. So knowledge is being shared, and that always allows a bigger group to move better.
And to riff on both of your points, I would say, firstly, our government clients certainly trend towards not having artifacts being public, but they definitely want to see everything. And so the openness actually helps with regards to them as a client and their assessments. The focus on interfaces is great because hardening an interface is easier than hardening the entire damn thing. So the openness of APIs, bus specs, et cetera, is where I think we'll see a lot of traction already. And there's government funding on that topic. But I will say that openness has nothing to do with something being actually secure, despite good intentions. If we continue to build systems the way we've done them in the past, if we continue to focus on features rather than on simplicity and elegance, and if we continue to ship things that are simulated and haven't been analyzed more deeply, perhaps using formal methods, we're going to be shipping a lot of stuff that we claim is secure, which is not, and that'll be embarrassing.
And we've been doing that for a long time.
Decades.
The other piece of this that goes along those same lines, though, is that if you are updating something and there's a vulnerability, that's great. The problem is when somebody finds a vulnerability, they don't necessarily publish that, particularly the bad guys. So now you have everything exposed that everybody else sees, but you also have stuff that goes on behind the scenes as well. Is that any different or any worse than anything else that's out there?
Security by obscurity has never helped so far. It's always been trouble more than anything else. So by publishing things, you get even more people that are able to look at it, and hopefully we can outrun the hackers a little bit. But by hiding things behind the scenes, it makes everything way worse because now you don't know what's going on at all. So maybe it gives the hackers a little bit of an advantage, but eventually the bigger group and the openness will achieve the goal better and faster.
Yeah, so I mean, I'll go back to what I said about we need some layers that are simple enough that they can be analyzed. Joe mentioned formal analysis. That's certainly a good way. A lot of eyes on it is another good way. But we have an advantage of RISC-V that we are going kind of down a formal route. We have a formal committee that's providing complete closed description of the language of the ISA interface, and then you need some additional things. In the software area, you can use like a microkernel like SEL4 that's small enough to be formally analyzed. But as soon as you get to something like a rich OS like Linux, you're never going to be able to fix all the bugs. And if you look historically, not the Linux example, but you look historically at set-top boxes and Sony PlayStation and whatever, a lot of these hacks work because the software on them was reverse engineered. And so I think there is a place for secrecy as at least a road bump to slow down the attacks.
The struggle I see is both. You did want us to talk, right?
Absolutely.
Okay. He told me to talk. The struggle I see is at the intersection of policy and technology. With our current leadership right now, there's a tendency to want to find and hold vulnerabilities close to the chest. So even if the government finds problems, especially with hardware, we're not guaranteed, even in the case of analyzing open systems, to ever hear about it. And that's problematic. So we need to continue to work as a community on helping inform policy, both legislatively and via the DoD and executive branch. But the flip side of that is, and a concern I hold, is that fixing vulnerabilities in hardware is manifestly more difficult than fixing them in software. And right now, I'm worried that we're seeing a balance of work that shipped products, especially those that begin to integrate hardware security features, are putting many of those features in non-updatable subsystems. So if you don't have, for example, microcode that can be updated with assurance, and you ship something after spending millions of dollars on design and fab, and the open community finds those vulnerabilities, we can harm ourselves as a community. I mean, VCs are going to be turned off by the fact that people are going to ship things that they claim are secure, are found to be insecure because we all love openness, and suddenly their products don't have some feature sets that they claimed. And I'm worried that that could have a knock-on effect on more prolific use of and aims towards security in our community in the medium term.
And I gather that's armed with a lowercase a.
Yes,
I think
sir.
I'd like to answer that one just for a short second. I think, proprietary designs, on the other hand, are also not really helping. They're going to be exposed to the same kind of issues. And once we find out that there's vulnerabilities there, just as this year has shown many, many, many times.
This week again, probably.
Again and again. In that case, it doesn't help because, it gets exposed and then you get, people propose patches and they don't work or they slow you down. And so it's not like we're not gonna have some of those issues as well. Of course, we will make mistakes and of course it'll be hard to change the hardware. But globally, we're better off because there's kind of more information available and we all learn from each other on how to do it better. So next time around we make it better, we can work together on solutions if there's any vulnerabilities being discovered. So making information public and open will always help in that direction rather than waiting until somebody actually finds a problem in proprietary solutions and then nobody knows how to fix it really well.
There's been a lot made about the security advantages of RISC-V because it doesn't have things like speculative execution or branch prediction, which were put into other chips in order to speed them up. Where do you see the weaknesses in RISC-V, though?
Well, I'm very optimistic for the future. I think we've, maybe dodged some bullets that some of the implementations we have weren't susceptible to specific attacks like Spectre or Meltdown. But that doesn't mean that these implementations aren't susceptible to some other timing analysis attacks. So there's a broad range, and especially since Spectre Meltdown came out, there's been a new attack published almost weekly, different kind of timing analysis attacks. So one of the things we've done in the foundation, we've set up 3 security committees. Helena and Joe are chair and vice chair of the standing committee, which reports directly to the board of directors. And so thank goodness the board has seen fit to elevate security to a top level concern. And I have great hope that we're going to be able to create RISC-V chips which don't have timing analysis type vulnerabilities in the future. So we have a little work to do. It's probably going to take us a few years, but I'm pretty confident that we're going to get there before people are working with legacy ISAs, which are a lot more constrained, and with our kind of clean sheet of paper, and with the knowledge we have today, I think we're going to be able to create much more secure chips in the future.
Yeah, I think we're also trying to simplify designs. There's room for making small secure processors, small hardware roots of trust, things like that, that will help you execute the security portions correctly on a separate space, and let the rest of the processing happen. There you could still have speculation and predictive branching and things like that. It'll be all fine as long as you don't apply that to computations that involve secret data. But so making it smaller, making it simpler, making it easier to understand is what's going to help us. So the weakness that remains here to be dealt with is probably at the implementation level. You can build your system correctly and you can hope to make it secure, but at some point you're going to have to implement it. And that's where it's getting more difficult. So getting help from people who know how to do this correctly will certainly be great. And then there's the other aspect of the RISC-V Foundation is that we do have vulnerable groups and compliance groups, and we're trying to build or assessing how to build tools and modeling that will help look at it from a security perspective and model security. And I don't want to overlap too much into what Joe is doing, but he can certainly talk more about that. So building tools that help assess security will be very helpful, and we're going to do that in an open way.
The main challenge I see is one of resources, literally human beings with the right set of expertise to contribute. Right? We have these working groups set up, but if you look at the core set of actors with the right set of expertise who are given the time by their companies or employers to contribute, there's basically 12 or 15 of us overall carrying the water for the entire community. We need more people to get involved. Therefore, we need more resources from companies willing to give people a fraction of their time, a day a week, for example, is a good level to be involved at. We also need more resources from government to help out with this. The SITH program that I perform on for Linton, who's sitting directly in front of me in the audience, is the first big foray from DARPA in this area, and it's been wonderful because he made an accidental brilliant choice in choosing RISC-V as the focus of the program, but that's completely incidental to the program's outcomes. It is meant to be applicable across the industry. So that's helping, but simply put, there's just not enough expertise with Slack. And so I think what should be done or could be done is those of you in the audience with expertise in hardware design, computer architecture, or physical design, who are really good at what you want to do, but want to expand your expertise area and your remit, and perhaps raise your paycheck, begin to learn about security. Talk to us working in these groups. Get involved, because by getting involved, you can learn from others and bootstrap yourself, and we'll happily help you out with that. And that will grow the community capable of contributing to the positive outcomes.
So call to action, please join, come and help us.
Come
We
help.
need help.
I will teach anybody in this room crypto in 2 days.
As a start.
As a start.
Some of the architectures that are coming out these days are, and some of the applications of where we're seeing these RISC cores showing up are related to things like AI, machine learning, deep learning. Those kinds of chips are very much a way of designing much faster chips, but they're based upon a much higher integration between the software and the hardware, and they're based upon, to some extent, the flow of data through these chips as a starting point, as opposed to the hardware being the starting point or the software being the starting point. How does that change security, particularly when these algorithms are almost in a constant state of flux and no two chips are alike?
You're definitely going to have to use some principles of least privilege and separation in order to be able to have processes which might not be considered secure or might have been compromised to be able to run alongside with your really core security protocols and key storage and crypto and things like that.
Yeah, I think if I look at machine learning and artificial intelligence, these are wide open fields. How to do that securely is a big open question anyway. So this is not exactly answering your question, but let me just, digress into a little bit of security related to that for a second. We don't know how to do computations on encrypted data that will help let a machine actually analyze things efficiently. We don't know how to do that today. There's a start of some research being done in that area. It's very computationally heavy. It's very complicated. Whether RISC-V can do it better than anybody else is a good question, but it's a very broad, open problem. And the other part is that we haven't even started looking at what it means to have malicious attacks in there. These algorithms, give them wrong data, treat it from a malicious perspective. Nobody knows what that means and what's going to come out of it. Or we all know that today we don't have the right answers. So this is a much bigger open problem that we're talking about.
My clients are very concerned about this problem because the DoD is very excited about AI in the field. And yet AI in the presence of adversaries, both from a data perspective as well as from a physical adversarial perspective, is a nascent domain. The early work I've seen that shows promise is people who design realizations of algorithms that pay attention to matters of security and are able to tag certain data as being secret and using information flow reasoning is one excellent sort of low-hanging fruit approach that's being used. There's quite a bit of funding on compute, like secure computation as well as homomorphic encryption, both in software and hardware, that's moving things forward, which gives you a bigger hammer to whack things with, but it's not always the right hammer. And it's also a very, very slow hammer. And then lastly, the new challenges that I see coming out that I would love to see action in this realm is, let's say you do have a set of AI algorithms realized in hardware and software, and they're being used for good purposes. We still have a fundamental problem that's open to this community as far as how do you have the hardware explain the answer that's given. So it's called Explainable AI, and there's several upcoming programs coming out of the government on this topic, whereby algorithms and their implementations have to provide evidence that the answer they've given is actually the right answer. And that's a wide open challenge. There's early work on it, but to my knowledge, very, very few people are trying to do or think about explainable AI in hardware. I encourage academics in the room who have received DARPA fundings in the past to begin learning about this now, because there's a big pot of money coming up on this topic.
And right answer there is a very vague term because you're defining accuracy based upon a distribution as opposed to an exact number, right?
Mm-hmm. Yep. All the early work basically focuses on the intersection of probabilities, essentially probability theory and programming languages. And now we're going to see the evolution of that, of probability theory and hardware design, which means you end up with, more often than not, mixed devices, digital and analog devices tackling these challenges.
So one of the issues with almost any security these days is that as more devices are connected, they may be connected to less secure devices. Even sometimes within the same system, we're starting to see more heterogeneous designs. Those heterogeneous designs may involve multiple vendors' cores, and they may be connected to other systems over unsecured links. How do you solve that problem? Is it one step at a time and everything has to be secure? People are going to find the weaknesses somewhere, or is it a system-wide, we need to really think about this from the top down and get all the vendors involved?
All the resources in the world can't do the latter, I'm afraid.
Right.
Especially given the burden we have on existing deployed systems that were never built to be secure, which includes, everyone's automobile in the room, developed in the last 12 to 14 years, and things like the F-35 fighter jet. These systems have fundamental insecurities in them. The work that we've seen go on is mainly about understanding those systems at a high architecture level and figuring out which key components sit at the center of a security assurance case, and typically building replacements for those components that can be deployed in the field. So replacing an existing widget with a new widget that doesn't cost $1 billion, but might cost a few $1 million, that raises the security assurance dramatically. We're seeing that in military vehicles. We're now seeing that in things that drive and things that fly that we all use. But it's still early days, and the fundamental problem with it happening is you don't see companies doing this until their customers care.
Yeah, I'll just reinforce those remarks that I think it's important we carefully draw the security boundaries around the things that we really can defend, and making everything totally secure is probably not going to happen in our lifetime.
Yeah, I think we need to look at it from a threat modeling perspective, right? Try to isolate the pieces in your system. Well, look at it as a system to start with. Do some system security analysis, and then try to isolate the components that you really care about, the ones that carry secrets, for example, the ones that run crypto operations, the ones that really should not be tampered with. Isolate those ones, make sure that those ones are secure, and again, simplify that part if you can. Now, I guess our background as a vendor is maybe not multi-million or billion-dollar systems, maybe smaller systems. And there's room, again, for tiny little secure processors to play their role, contain all the keys, do the crypto computations, do the security part of it, and then let the rest of the system do its own parts. But yeah, it's a complex problem.
No matter how good you make this, though, there are still things you can't see or know. For example, there are weaknesses where you design a system and it's not perfect. Maybe that allows something to creep in that you didn't expect, or you have a problem that shows up later on with an AI type of system where it changes and you didn't expect it to change that way, and that creates a new vulnerability. At this point, these things are opaque. There's no way to understand what happened, go back and find out, here's what caused this problem, we can close this up, because a lot of these algorithms are changing so fast and they are themselves opaque. How do we solve that? This is one where I don't expect an answer, by the way. But.
Well, there always has to be, you always have to have a roadmap of things that can evolve. No system will ever stay static and be secure for the rest of time. It's always been a race, a battle against, new people coming up with new attacks. So you try to understand what the new threats are, what the new security weaknesses are that get discovered, and then you try to counteract by putting out new versions and updates and upgrades and whatever you can do, which in hardware isn't that simple. But whatever you can do to take care of these new style attacks. So be aware that it's not a static game. It's always one against the other. It's always going to move. The target is moving all the time. And be prepared to have to change your implementations, change your approach every single moment, so to speak. So have a roadmap ready. But yeah, it's going to continue to evolve. It would be boring otherwise.
The work I see that holds the most promise is doing firmware, hardware co-design with an assurance case so that you do have the ability to pivot as things move forward and we don't see the deployment of new hardware as we have seen, for example, from ARM and Intel over the past decade, where new large-scale security features are introduced in new chips, but they have little ability to pivot once vulnerabilities are found. You end up with essentially dead hardware or useless hardware. So as we see more and more careful attention to formal specifications and reasoning around microcode and firmware so that we can shift functionality and bake into the design the ability to evolve the hardware, that's where I see promise.
You're talking about sort of bare metal type of programming there?
Not necessarily. I mean, insofar as the firmware can be often realized as bare metal programming, yes. But in the main, no. I'm mainly talking about having a system like produced by Microsemi, for example, that gives you, or even you guys, about having some measure of attestation around not just core hardware on measured boot, but also the necessary firmware there so that you can have an evolutionary path to mitigating quickly in the field.
Yeah. The more complex the system is, the more likely it is to experience these problems, the more important it is to be able to pivot or update the firmware securely. On the other extreme, you probably still need some core root of trust in the system that's small enough, and that's going to be very hard to change. And so that's where something like formal analysis can help you receive a high security assurance for that central part.
I got to say, a fear I have is that we get a bunch of RISC-V systems deployed with patchable security in a sense, and we have large IT corporations who tell their IT staff never to patch the firmware. Because that's what we see today, and software is a lot more easy to patch than the hardware is in some sense. So my fear is that we're going to bake this into our architectures, and then business pressures are going to lead to systems being never upgraded.
Well, most of the patching that's been done so far has typically been up a couple levels of abstraction, right? It's typically either at the operating system or above the operating system level. You're
That's
talking
true.
substantially below that.
Indeed, which makes them more fearful, not less.
Right.
Start with a small hardware piece, right? That can be as small and simple as possible. Try to prove as much as you can on that one. Make sure it has hooks in there to be able to update and upgrade whatever runs above, and then make the rest as programmable as you can, so that you can, build layers of security up until application level, and that you can change along the way whenever you have to. But yeah, the core has to be small enough that you can essentially fold up from there.
Joe, building on something that you said here, in the past there's been a lot of interactions between industry and academia and between academia and government, but it's rare that you have all three of those in the same bucket. Does that have to change? Is it changing in order to solve some of the issues that we're talking about here?
It's critical that it happens, but it's also critical that we understand that those different actors have different value metrics, shall we say. We're seeing quite a bit of change, especially over the past decade with government funding. We see more and more teams that are excellently balanced between commercial firms and academics worldwide. I'm also encouraged to see more and more academics from outside the US getting funding with US funding, at least in countries where we're friendly. Because the set of expertise worldwide is vast. There's a lot of great people in Europe and Israel and the like who can contribute to the outcomes of the security community overall. But the main thing that we need to realize and leverage is that when I was a professor, I had a different value metric. I was awarded and promoted based upon publishing papers and raising research grants, not shipping products, though I still shipped products because I was a dumb guy. Whereas at a company, business and customers is what drives you. So we need to make sure that as funding opportunities continue to appear, one, academics and companies who haven't pursued funding through these sorts of channels begin to do so. So it's a shifting of where you're getting your IRAD funding. And two, recognize the fact that academics should never be in the hot path to shipping a product. They should do what they'd love to do, write papers, publish prototypes, and then have the companies be able to take that edge research and turn it into product. And I'm very encouraged by the RISC-V community because we're seeing it here more than anywhere else in my lifetime of work spanning the world of hardware and software. The openness of the foundational ISA and the fact that it came from teams that can ship product like Berkeley and others really has set us on a good trajectory.
Yeah, I think we have a great opportunity to do it right here. There's been one example, at least I can think of, where it's worked really great before between academia, industry, and government. Typically, not all the entities work together, but at least, for example, for the AES competition, which is pure crypto competition, that has worked really well. So designs have been proposed actually by somebody who was both in industry and academia. The rest of academia and industry has looked at it and has tried to come up with cryptanalysis methods, try to direct the choice to the right one eventually, but it's all been standardized and driven by government-oriented organizations or organizations that actually standardize technology. So that has been a great success before, and I sure hope we can do it again with RISC-V, because this is the right time to get together and kind of, even if each one of us, whether it be academia, industry, or government, has slightly different goals, we all want to make it more secure in the end. And so we should be able to come together to do that.
One of the things I see about RISC-V is that because everybody in effect has an architecture license, we're spurring a lot of innovation. And that's happening in security as well. So we see quite a few people doing many different approaches on security. And I see RISC-V in general and the foundation activity as kind of being the center of CPU-related security research. So this is a place where everybody can come together and work on security and able to innovate, work with people from government, from academia, from industry.
I'll say that we're going to see an explosion of outcomes on this topic, because this SITH program that I perform on for DARPA concludes its first phase in March. And therefore, there's a number of papers in the pipeline focused on different approaches to security for CPUs and SOCs that happen to use RISC-V artifacts that will be published in 2019. And moreover, many, if not all of those designs are going to become public next year. And so we're going to see a real flowering here. And those of you who aren't participating in these programs can directly learn from, riff upon, or use those designs if they're appropriately licensed. So my expectation is the next wave of RISC-Vs that we see coming out circa late 2019 and 2020 will use one or more approaches that spin out of that program. It'll have a huge impact.
Now that you guys are all relaxed, I'd like to ask a different kind of question here.
Do we get to fight now?
When does it start?
So one of the issues with RISC-V is that, or one of the advantages of RISC-V is that you can play around with the source code in a way that you can't do with a lot of other chips that are out there. How much of a risk does that open up in terms of things like backdoors, which we really haven't had to worry about in the past? I think only the government really worried about it.
I think
There's plenty of backdoors.
I think inspectable code is a good thing for RISC-V, and maybe as Joe said, maybe the whole world doesn't inspect it, but at least your customers can inspect it, or somebody your customer trusts can inspect it and give some assurance that there's no Trojan horse in your design.
The great fear I have is that even though our RTL designs are transparent, our EDA tools are not. And, a previous Turing Award winner gave a whole talk on what happens when your compiler is compromised. So a great fear I have is that, and it is a core concern for the DoD and especially the IC, is that because those tools are opaque, we have little to no confidence that the masks we send out actually don't have backdoors in them. And there's quite a bit of research on that topic right now. So I'm encouraged by, for example, Andreas's program on IDEA and POSH, where we can get some more transparency around that tooling and therefore have a more transparent assurance case when it comes to these matters in the next few years.
Yeah, there's definitely progress being made in that area, at least in some realms.
Yeah.
But it is a challenge and a concern.
So we need another foundation to deal with open source EDA tools then?
We'll see where that spins out. You can talk to Andreas about it.
But so to come back to your backdoor question, just 1 second, I don't think you can, you can't really stop people from putting backdoors somewhere if they want to. Now, opening up the source code can only help try to look at it, try to review it, and trying to make sure there is no such thing in there. It's difficult because it's a lot of code, and it's not easy to formally analyze if there's anything weird in there, but at least you open it up. By not opening up, it makes it even more complicated. But then again, if somebody wants to put a backdoor somewhere, it's going to be very hard to disallow that anyway. They can always do that.
It sounds like a good contest for next year, right? Soft core vulnerable CPU contest where we see who can come up with the most creative backdoor. Yeah, I know. I'm a troublemaker.
Find the Trojan.
Yeah.
Is RISC-V starting to get into safety critical type of applications such as industrial or automotive or medical? Is it finding its way in there yet?
If it is, we can't tell you.
I don't think there's any particular reason not to, right? RISC-V is great, and it can help build small security processors for any type of application, whether it be automotive or anywhere else. You have ECUs in there that can be based on RISC-V. You have, gateways in there that can be based on RISC-V. There's no reason not to go there. On the contrary.
Yeah. I see companies going that direction, at least in specific industries, but it's maybe fits and starts because they have quite a bit of momentum around previous products and knowledge around more antique ISAs. On the government side, I don't see much motion. There's so much momentum in the existing military-industrial complex around different kinds of architectures and chipsets that I haven't seen anybody yet move on RISC-V to help out that side of the business. It'll happen, but I don't think I'll see it in the next couple of years.
Well, the big vulnerabilities that were shown up on that came out with Spectre Meltdown, those showed up out of Google Project Zero. Have they taken a look at RISC-V as well, or is this still the community is doing this and nobody else has looked at it?
Well, Google's here, and they're working on some RISC-V related stuff. As far as I know, the Project Zero team isn't particularly biased in this direction because their tools and techniques are sort of ISA neutral. But I wouldn't be surprised if that evolves. There are other similar red teams who utilize reasoning techniques to find vulnerabilities that are focusing on RISC-V on occasion, including sometimes in my company.
Yeah, I think in those kinds of attacks, we're just at the infancy of this. So any target is good to go after because it can only help be more secure afterwards. Mm-hmm. But we'll see more and more of these things getting published and found. So the beautiful part of this is that if we look at RISC-V and if there is anything there that we want to talk about, we can do it. That's what we're here for. That's what we have the security committees for. And this is exactly the type of discussion that we would like to have.
I'd like to thank our panelists. Thank you all for coming.